So this is another example of Lagrange multipliers. In this case, we're looking at finding the maximum and minimum values of this function p, subject to the constraint x squared plus 2y squared equals 3. So that is, of all the xy values that satisfy that constraint equation, what is the maximum value that we can get for p if we take those xy values as input? So we think of restricting p to the inputs coming from the constraint. What is the maximum value p can take on? So there's a picture of this drawn. What I've sketched out is the constraint in green. So that's basically an elliptic cylinder. And we are interested in only the points that have xy value satisfying that cylinder. So this is really a curve in the plane, if you will, in the domain, the xy plane. But I've extended it with an arbitrary z value to be a cylinder. So of those values x and y that live on this cylinder, what is the maximum value we get on the blue surface? That's the graph of this paraboloid that we get for p for paraboloid in that case. So this is a Lagrange multiplier, or this can be interpreted as a Lagrange multipliers question. We can attack it using the method of Lagrange multipliers. And the way we're going to do that is we're going to first note that this is our constraint. So we have that g of xy is equal to x squared plus 2y squared minus 3. And the constraint equation is that g is equal to 0. The way we go about finding the extrema is the method of Lagrange multiplier says that the gradient of p has got to be parallel to the gradient of our constraint. And so that gives rise to three equations. Actually, two equations in this case, because there's only two variables, the x partial and the y partial equations. And then we have that third equation, which is our constraint. So let's jot down these three equations. So p sub x is equal to lambda g sub x. We get a second equation, p sub y is equal to lambda g sub y. And we get our last equation, which is our constraint, x squared plus 2y squared is equal to 3. And so these are the three equations we're going to solve for the three unknowns, x, y, and lambda. So what is p sub x? That's the derivative with respect to x. So that's 2x plus y is equal to lambda times the derivative of g with respect to x. So I'll bring this constant 2 just in the front here. This is 2 lambda x. Do the same thing for the y derivatives. We get an x plus 4y minus 1 is equal to 4 lambda y. And so there's our two equations. We'd like to solve all three of these equations simultaneously for x, y, and z. There's really no method for doing this other than just depending on the equations you're given, you just try whatever techniques you can. So for us in this case, I'm going to notice that I've got a lambda x and a lambda y on the right-hand side of these two equations. It would be nice if it was a lambda xy in both cases. So that's what I'm going to do. I'm going to scale through. I'm going to scale through this first one by a y. 2xy plus y squared is equal to 2 lambda xy. And I'll scale through the second one by x. X squared plus 4xy minus x equals 4 lambda xy. Move this bar over. Lambda xy. And now that I have this common xy in both cases, I can effectively set these things equal to each other. I have to worry about the scaling factor in front. In fact, what I will do is I will say that these are both essentially 2 times lambda xy. So I'm going to group the 2 in there with it as well. That's a 2xy. And this one is almost a 2xy. It is actually a 4xy. So I will borrow one of those 2's to join it with that and put the other 2 out front. And so at this stage, I can say now I'm going to take these 2 equations and I'm going to get that 2 lambda xy is equal to 2xy plus y squared. Well, if I multiply that one by 2, that makes that equal to a 4 times lambda xy, which is exactly what the other side or the other equation is equal to. So we get this equality. So I'll do a little bit of cleanup. We get a 4xy plus 2y squared is equal to x squared plus 4xy minus x. Oh, I get the 4xy's canceling. I get an x squared minus x is equal to 2y squared. And then at this point, I can say, well, that equation, the constraint, I can now use to replace that 2y squared with something involving x. So if I use the constraint, I get x squared minus x is equal to 2y squared is 3 minus x squared. And so I get 2x squared minus x minus 3 is equal to 0. Okay, and now I just need to solve for x. Now I've got a single equation with variable x in it. You can see if we can, maybe we're lucky, maybe we get factorization. If not, we use the quadratic formula. So I'm going to have a 2x and an x, and that's going to give me the 2x squared. Then I need to get that negative x, and I also need to get negative 3. So maybe I'll have a 3 here and a 1 here. I'm just sort of playing around with this and seeing what I get. 2x times a 1 gives me a 2x, and then I get a 3 times an x, which is a 3x, but I want it to be negative, so I think I want the negative there and a plus there. And then I'll do a quick mental double check. 2x times x is 2x squared. 2x times 1 minus 3x is negative x, and negative 3 times 1 is negative 3. So perfect, we got our factorization. Therefore, we got that x is negative 1 or 3/2. Okay, we're in good shape. We got our x value. Now we can get our y value. What's our y value going to be? Well, we can use this equation, which relates x and y, or we could use the original constraint. Either one would be fine. This equation that I'm writing down tells me that 2y squared is equal to x squared. There's actually a couple of x's to deal with, so let's deal with those. X equals negative 1. That's our first case. So we get that 2y is equal to negative 1 squared minus 1, which tells me then that 2y squared is equal to 1 plus 1, or y is equal to plus or minus 1. Okay, excellent. So we got x is negative 1, y is plus or minus 1. Let's actually just write that down. Therefore, xy is equal to negative 1, y is plus or minus 1. What about the other case? X is equal to 3/2. 2y squared is equal to x squared, so 3/2 squared, minus x, which is 3/2. Again, I'm just using that equation that sort of I drew the arrow down here for. And that's going to be 9/4 minus 3/2, or 9/4 minus 6/4, or in other words, 3/4. So that tells me that y squared is equal to 3/8. In other words, y is equal to plus or minus root 3 over, or maybe I'll just write it as root 3/8. So there's our y value for that. And so therefore, we've got that xy is equal to 3/2 and plus or minus root 3/8. So there we go. We've got all of our values that we could have potential extrema at. Now we just have to figure out where is the maximum and where is the minimum. So in order to do that, we can go ahead and just work out the values x, y, and p of x, y. So we've got a -1, -1, sure, we'll do that one first. -1, 1, 3/2, negative root 3/8, and 3/2 positive root 3/8. Those are our 4 points. Work out the corresponding p-values. Leave the details of that calculation for you. We get p of 5 for the first point, p of 1 for the second. For this one, we get a 3 plus 1/2 root 3/8. And for the other one, we get a 3 minus 1/2 root 3/8. Now, the thing is that we are actually, on a region. So if we think about our constraint and our plot here, we are trying to find the maximum value of a point on this black curve, this intersection curve, because that's going to be a point that satisfies the constraint, and we're trying to find the highest point. So in other words, maximize the p-value. What we have found is we have found 4 points, one over there and one about here. Once we found those 4 points, we're just going to figure out which one's the biggest, which one's the smallest, and we've already listed their values. So we can see from here that this one is the maximum and this one is the minimum. And so the maximum value of p is 5, and we've got the point it occurs at. We could also get this information from the level curves as well. So sketched on the right is the level curves for our function p. It's a paraboloid, so you can see those. It's elliptic paraboloid, so you can see those concentric ellipses. Those are our level curves. And the green curve is our constraint. So again, one thing to notice about our constraint is as we move along it, if I'm moving across one of these level curves, say where I'm crossing the blue level curve, this is a paraboloid, so it's opening upwards. So as I move outwards, these concentric ellipses have larger values. They're higher up the surface. And so as I move along this green curve and I cross the blue ellipse from its inside to its outside, my z value is increasing. So I'm going up, up until I hit a point of tangency with this level curve, and then I start to decrease again. And so what we have detected are these points. I'll indicate them here. We've detected that point, that point, that point, and that point. And furthermore, what we've detected is that at -1, -1, so that's this point down here, we've got a max, has a value of 5. We also had -1, 1. This point up here was our minimum. And then we had a couple of these other points as well. These were our local max and our local mins. So this is our local max, and this is our local min. Why is that one a local max, for example? Because I'm increasing up to it and then turning around and coming back down. I'm inside that level curve. So I'm always at values lower than the point of tangency. Whereas with this one out here, I'm outside the blue level curve. So I'm always at values slightly higher, but I come down, hit the point of tangency, and then go back up again. So that's our local min. Similarly for the other ones, that's why they're maximum minimums, but they end up being absolutes. In this case, absolute max and absolute mins, because those are the corresponding values, in which case we get the extrema All right. Okay, so that's it for this example.